We'll now take a look at section 12.2, which deals with permutations and combinations. So if we remember back from the last section, the counting principle stated that the number of ways that a multi-step experiment could be performed was found by multiplying the number of ways that the first part could be performed by the number of ways the second part could be performed, etc., depending on how many parts of the experiment you had, right? So like we had that one example where you were choosing a history class, a art class, and a economics class. So those were the three parts, and you just had to multiply how many choices you had inside each of those parts, and that was the counting principle. So with most of those situations, the parts or the steps of the experiment were what we call independent events. And what that means is that the result of one of them didn't have any impact on any of the others. So the only exception to that was if we had a card problem where we were drawing cards without replacement, then that was what we call dependent events. But when we do these permutations in a minute, what you'll see is that these are going to be what you call dependent events because, you know, the result of the first step definitely impacts the next step. Okay, so just before we get into permutations, just another quick example of the counting principle. How many different computer passwords of 2 digits followed by 2 letters could be created, right? So if you think about this, this is really like a 4-step experiment. You have 2 digits, so that's 2 steps, and then you're going to have 2 letters. So you remember how we had done this with the counting principle? We did the slots and choices. So you have 4 slots. So the first slot would be for the first digit, that's digit 1. Then the second slot would be for the second digit. Then the third slot would be for the first letter, and then the last slot would be for the second letter, right? And then you just had to see how many choices you had at each of these steps. So there's 10 digits, right? 0 through 9. So you'd have 10 options for the first digit. They don't say anything about how you can't reuse a digit, so we would still have 10 options for the second digit. And then for the letters, well, there's 26 letters. So the one thing that's kind of unclear here is, are they saying you could use a capital or a lowercase? So technically, if you could use a capital or a lowercase, you would actually have 52 choices for each. But let's just assume that we're just dealing with a single case here, like let's say lowercase. So there's 26 letters. So you'd have 26 choices for the first letter, and then you'd have 26 choices for the second letter. And then if you multiply all these things, that's going to give you the total number of passwords, right? So you just do 100, right? Because that's 10 times 10. So 100 times 26 times 26, and that's going to give us 67,600. So there's 67,600 possible passwords that are 2 digits followed by 2 letters. All right. Now, the difference though is when we perform these multi-step experiments without replacement, meaning we can't reuse something that we just used, what's happening is our options are dwindling down, right, after each step. So when we have this situation, we're going to use what are called permutations, right? And permutations are really just ordered arrangements of a given set of objects. And the key word there is ordered. Order matters here when you're doing permutations. So let's say I wanted to order 5 objects, right? That would be written as 5 with this exclamation point after it, which would be read 5 factorial, right? So when you see that exclamation point, what you say is factorial, right? But it really means a permutation of 5 objects arranged 5 at a time, right? So 5 factorial, what it means is 5 times 4 times 3 times 2 times 1, right? Which makes sense because this, if we think about this in our slots and choices idea from before, you would have 5 slots. For the first slot, you'd have 5 choices, then you'd have 4 choices, then you'd have 3 choices, so on, right? So if you're doing 8 factorial, that means you're arranging 8 objects, 8 at a time. So you'd have 8 choices for the first slot, then 7, then 6, then 5, then 4, all the way down to 1. Okay, so 8 factorial is just 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But again, you can really think of it as slots and choices again. That's another way of thinking about it. So if you were asked to find the number of ways a president, vice president, not vice president, vice president, right? Vice president, secretary, and treasurer can be chosen from a group of 4 people, that means in this case, everyone is getting a position, basically, right? Because there's 4 people and they all have to have one of these positions. So if we think about this in terms of slots and choices, we would have 4 slots, right? You'd have a slot for a president, vice president, secretary, treasurer, right? So the first slot would be president, then VP, then secretary, then treasurer. And for the first slot, you would actually have 4 choices. But now for the second slot, someone's already been chosen president, so now you only have 3 choices. Then for the secretary slot, 2 people have been chosen, so you only have 2 choices. And then for the treasurer, you basically are stuck with whoever's left, right? So you would do 4 times 3 times 2 times 1, which is really 24. So there'd be 24 ways that president, vice president, secretary, and treasurer could be chosen from a group of 4 people. And you could have just bypassed that if you just had recognized it immediately as, okay, this is a permutation of 4 objects taken 4 at a time, right? So it's really just the same as 4 factorial. Okay, and just as a note, if you have a calculator, whether it's scientific or graphing, there is a way to do the factorial on the calculator. On the graphing calculator, you actually have to press the math button, and then you go over to where it says PRB, which basically stands for probability, right? So we're doing the exclamation point, which is factorial. So if we wanted to do 4 factorial, we type 4, then we go to our math button, down to probability, and we'd hit the exclamation point. So 4 factorial is 24. So we can do this on the calculator. All right. So now in that one, all of the people had a position, right? We used up all 4 of the people in a position. But let's say there's a club or something like that, right? Or some organization that has 12 members now. Now they're all not going to get a position. So in this case, you're still choosing a president, a vice president, a secretary, and a treasurer. But now what's happening is they're not all going to get a position. So you would still lay out your 4 slots, right? You'd have a slot for the president, for the vice president, for the secretary, and the treasurer. But now you're choosing from 12 members, right? So you're arranging 12 things, but you're only arranging them 4 at a time, right? You're not arranging all 12 of them. So for the first slot, you would have 12 choices. Then you'd have 11 choices. Then you'd have 10 choices. Then you'd have 9 choices. So that's actually 12 times 11 times 10 times 9. And what that's going to be is, that's going to be 11,880, right? So obviously there's a lot more possibilities here because not everyone's getting used. So 11,880 ways that you can choose those 4 positions from 12 people now, right? That's a lot of ways. All right. So there is actually another way to write that in terms of a permutation. Because remember how I had said just before, I can think of that as arranging 12 things 4 at a time though, right? So I'm taking 12 things and arranging them, but only 4 at a time. So 12 things 4 at a time, right? Ordering or arranging 12 things 4 at a time, you could write that as P and then in parentheses 12 comma 4, or the way it's normally written, more likely, is this 12P4. All right, and here's the definition of what 12P4 would be, right? It's actually 12 factorial divided by 12 minus 4 factorial. But if you look at that, let's say I was going to write that out, right, in the strict definition form, 12 factorial would be 12 times 11 times 10 times 9 times 8 times 7 times 6 times dot dot dot, right, all the way down to 1. And then 12 minus 4 factorial, right, I would do the parentheses first. So this would actually become 8 factorial. And then I would do 8 times 7 times 6 times dot 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 down to 1. So look what would happen here in the definition. these are just factors, so you can cancel them. So this 8 would cancel with this 8, 7 cancels with that 7, 6 cancels with that 6, 5 cancels, 4 cancels, 3 cancels, 2 cancels, and then 1 would cancel. So look what would be left. It would just simplify down to 12 times 11 times 10 times 9, which is what we just had in the last problem, right? And what was that again? 11,880? Yeah, 11,880. Okay, so the easy way to remember it is it's really just the first 4 factors of 12 factorial, right? So the 12 factorial will be 12 times 11 times 10 times 9 all the way down to 1. But if you're only taking the first 4 factors of that, it's just 12 times 11 times 10 times 9. So then something like 8 objects arranged 6 at a time, you would write this as 8p6, right? Or it would be p 8 comma 6. This is the more common notation though, 8p6. So what would this be? Again, if you wrote it out in this strict form, it would be 8 factorial over 8 minus 6 factorial. But what's going to happen is this is just going to end up boiling down to the first 6 factors of 8 factorial. And the first 6 factors of 8 factorial would be 8 times 7 times 6 times 5 times 4 times 3, right? Because the 2 and the 1 would cancel out down here because the denominator would have been 2 factorial, so the 2 and the 1 would cancel. So you would have just had 8 times 7 times 6 times 5 times 4 times 3. And again, luckily, the calculator can also do this for us. So the way we would enter 8p6 on the calculator is we would type the 8, then we would go to our math button, over to probability again, and you'd go down to number 2, NPR, and then you would type the 6. So 8 NPR 6 is going to be 20,160. So in this case, we end up with 20,160. And again, you can verify that if I did 8 times 7 times 6 times 5 times 4 times 3, I get the same answer, right? So it works out doing it either way. I actually personally prefer the slots and choices method. I think that's the easier way to think about these permutation problems, because then you don't have to worry about thinking about the different notation, right? How do I write it? Is it factorial or is it, p? I don't know, right? So that's the basic intro to permutations.